Hi, everybody. In this video, we're going to go through some increasingly complex examples using trig substitution. If you would like to skip to one of these examples, you can find a link in the description. The tell for when you want to use a trig substitution is when you see generally the square root of a quadratic function and no other obvious substitution. So you'll see all of these involve square roots of quadratic functions. When we do trig substitutions, we want to keep in mind these three identities, two of which are, of course, the same, just rearranged. Let's look at this first example. The quadratic equation down here is 1 plus something squared. So we're going to check out our identities in the top and see which one looks like 1 plus something squared. This is 1 minus something squared. This is 1 plus something squared. And this is something squared plus 1. So we're going to use that middle identity. 1 plus tan squared is secant squared. My goal is for my quadratic term to turn into 1 plus tangent squared. So the substitution that I should use is x is equal to tangent of theta. So what I'm doing here is I'm defining a new variable theta, and this is its relationship with tangent. If I'm doing a substitution, of course, I also need to find dx. So in my substitution, 1 plus x squared becomes 1 plus tan squared theta, still raised to the power 3/2, and dx becomes secant squared theta d theta. Always remember, we don't just get to say dx is d theta, we need to glue something to d theta. Now, the reason I wanted to do this is because now I can use my trig identity down here in the denominator. 1 plus tan squared is the same as secant squared. So this is secant squared theta raised to the power 3/2 times secant squared theta d theta. And the reason why I wanted to do that is now this root and this power 2 are going to cancel out, and we'll be left with 1 divided by secant theta cubed secant squared theta d theta. Now, in general, if I take the square root of something squared, it's actually equal to the absolute value of that thing. But for technical reasons that we're not going into, when you do these three trig substitutions, you can assume that everything is positive. Now I'm left with a trigonometric integral. So I'm going to simplify this a little bit. This is 1 over secant theta. And 1 over secant theta, remember, is cosine. So I started with something that I didn't necessarily know how to integrate, and now I've got something that I can absolutely integrate. The antiderivative of cosine theta is, remember, positive sine theta plus c. Now that we've gotten our calculus out of the way, it's time for a trigonometric portion again. Theta is something I made up, so I need to get everything back in terms of x, and to do that, we're going to use a right triangle. When we defined theta, we said it is an angle whose tangent is x. So let's draw an angle in a right triangle, call it theta. I know the tangent of theta is the opposite over the adjacent, and I know that that's x, which is the same as x over 1. So I'm going to take this opposite side here and label it x, this adjacent side here and label it 1. What I want to know is sine of theta. Sine is opposite over hypotenuse, which means I need to figure out the hypotenuse. And the hypotenuse I can figure out using the Pythagorean theorem. This is going to be the square root of 1 plus x squared. So then sine of theta is opposite over hypotenuse, which is x over root 1 plus x squared. So this turns into x divided by the square root of 1 plus x squared plus c. And that is my antiderivative. In this example, once again, we have the square root of a quadratic function, no obvious other substitution. So this tells us we want to use a trig substitution. I have the form function squared minus a constant. This is constant minus function squared, which is backwards. This is function squared plus a constant. This one is what I want. Function squared minus a constant. So this is the trig identity that I want to use. Sec squared minus 1 is tan squared. When I do my substitution, I can make x into whatever I want. I define the theta that works with x, but 4 is just going to be 4. So what I'm going to need to actually do is I'm going to need to multiply my identity by my constant so that it's going to work out. So I'm going to multiply the left and right side of this equation by 4. 4 secant squared theta minus 4 is equal to 4 tangent squared theta, and that is the form that I'm going to use this identity in. So what I want now is I want to match x squared minus 4 to 4 secant squared minus 4. I want to find a substitution for x that will turn this into that. So the thing that I want is I want x squared minus 4 to turn into 4 secant squared theta minus 4. So add 4 to both sides. X squared should be 4 secant squared theta. Square root both sides. I'm going to choose 2 secant theta. In principle, you could choose negative 2 secant theta, but why make your life difficult? All right, we're going to be doing a substitution, so I need to know what's going to happen to dx, so I differentiate on the right. The derivative of secant is secant tangent. So 2 secant theta tangent theta d theta. This is going to be the trig substitution that will allow me to get rid of that square root. So let's carry it through. 1 on the top is 1. X squared is now 4 secant squared theta. 4 is still 4. And dx turns into 2 secant theta tangent theta d theta. In the denominator, I can use my identity. That was why I chose this substitution. So 4 secant squared theta minus 4 is 4 tangent squared theta. And then I still have 2 secant theta tangent theta. And now, this is the whole point of this method, I get to cancel out the square and the square root. I couldn't do it here. Couldn't do it here. I can do it here. So my numerator is still 2 secant theta tangent theta. My denominator is now 2 tangent theta. So I no longer have that square root. Now I have a trig integral. 2's cancel, the tangents cancel, and I have the antiderivative of secant theta d theta. And this is something to memorize. This is the natural log of the absolute value of secant theta plus tangent theta plus any constant. Okay, so our calculus is done. We've performed a u substitution, which turned an integral we didn't know how to evaluate into an integral that we do know how to evaluate because we've memorized how to do that. Now it's time for trigonometry. Again, theta is my own personal invention. I need to get my, my function back in terms of x. So we can do that by using the definition of theta. This line here is where I said, I'm going to define a new variable theta, my own invention, and this is its relationship with x. So from my definition, I see that x divided by 2 is secant theta. So this is easy enough. This is x over 2, but I still need to find tangent of theta. So again, one way of doing this is to draw a right triangle. Now secant theta, that's 1 over cosine, so that's hypotenuse over adjacent. So in my right triangle with angle theta, I'm going to label the hypotenuse as having measure x and the adjacent side as having measure 2. For the tangent of theta, I need the opposite over the adjacent. So in order to find the opposite, I'm going to use the Pythagorean theorem. The opposite side is going to have measure square root of x squared minus 4. So that tells me that the tangent of theta, which is opposite over adjacent, is the square root of x squared minus 4 divided by 2. So now I can come back here to my antiderivative and I can rewrite this as the natural log of the absolute value of secant of theta is x over 2. And I found that tangent of theta is the square root of x squared minus 4 divided by 2. And this is the antiderivative of that function. Onwards and upwards, we have the square root of a quadratic function. But the thing we want to check before we do a trig substitution is there not perhaps an easier substitution? If I were to let u be this quadratic function, then its derivative would be some constant times x. And that shows up multiplied by the function. In particular, it's multiplied by the function in such a way that I can glue it to dx. So this tells me I actually don't want to do a trig substitution. Now you could use this method and it would work, but it would be long and unnecessarily painful. So instead, let's recognize that this is a substitution problem that does not need trigonometry. I can let u be 9 minus 4x squared. Then du is negative 8x dx. I have x dx, so I'm going to multiply both sides by negative an 8. And then negative 1/8 du is x dx. So when I do my substitution, this x dx I'm going to glue together, and that's going to turn into negative 1/8 du. So here's negative 1/8 du at the end. And then in the middle here, I've got 1 divided by the square root of 9 minus 4x squared. So 1 divided by the square root of u. So altogether, I have negative 1/8 u to the minus 1/2 du, which I can evaluate using the power rule if I like. So I'm going to add 1 to my power. Minus 1/2 plus 1 is positive 1/2. And I'm going to divide by 1/2, which is the same as multiplying by 2. So this is negative 1/4 times the square root of u. Of course, there's a plus c here, which works out to negative 1/4 times the square root of 9 minus 4x squared. They say to a person with a hammer, everything looks like a nail. So do keep in mind, it is not every time you see the square root of a quadratic function that you need to use this high-powered machinery, this hammer of trigonometric substitution. This one, though, you do. So I have a square root of a quadratic function, and there's not an obvious substitution because if I let u be this, I need x multiplied by dx to be my du in the way that x was multiplied by dx here. And here I don't exactly have that. I have x in the denominator. So you could maybe try pretty hard to shoehorn this into a u substitution, or we can just go ahead and use trig substitution. So first off, we need to choose which of our 3 favorite identities we're going to be using. I have a constant minus a squared function. So we need to match that up. This is a constant minus a squared function. That's good. This is a constant plus a squared function. No good. This is a squared function minus a constant, which is backwards. So we're going to be using the sine and cosine identity. Now, I can make this term with x into anything I want by choosing the appropriate value of x, but this 2 is just going to be itself. It's not going to be affected by a substitution. My constant needs to be 2. So in my identity, I'm going to multiply both sides by 2, and that's the form of the identity that I'm going to be using. I'm going to be using 2 minus 2 sine squared theta is 2 cosine squared theta. This is the form I'm going to be using the identity in. Now I have these 2 things which turn into one thing. I would like these 2 things to turn into one thing as well. So my goal for my substitution is that 2 minus 5x squared should turn into 2 minus 2 sine squared theta. And so I can use this to figure out what my substitution should be. This tells me 5x squared should be 2 sine squared theta. So x squared should be 2/5 sine squared theta. So I can let x be the square root of 2/5 times sine theta. Again, if you were really feeling like it, you could try and make this work with negative, but why? Okay, if I'm doing a substitution, I also need to know what's going to happen to my dx. It's going to be the square root of 2/5 cosine of theta d theta. So with that set up, I'm now at the point where I should plug these into my function. I should perform that substitution. So my integral turns into 1 is just 1 divided by, what's x? X is root 2/5 sine theta. And then what goes underneath the square root? 2 is a 2. Minus 5 times x squared. What do I get when I square x? I get 2/5 sine squared theta. So I've translated this, I've translated this. The last thing to translate is dx. Dx turns into root 2/5 cosine theta d theta. Okay, so let's clean this up a bit. Root 2/5, that's nice. In the denominator, let's see, I can put this cosine up top. I've got sine theta times the square root of 2 minus, the 5's cancel, and I have 2 sine squared theta d theta. And now I have gotten to where I had hoped I would get. Now, by the way, you can often skip straight to here if you're confident that you did this correctly, but plugging in everything starting at x is a nice way of checking your work, that the fact that I got to the thing I wanted to get to means I didn't make any algebra mistakes. And the reason I wanted to get to that is because I can use my trigonometric identity to turn this into a perfect square, 2 cosine squared x, 2 cosine squared theta. All right, now, moment of truth. I can cancel off this square root and that squared. And again, this is the entire purpose of our u substitution, of our trig substitution. So this is the square root of 2 times cosine theta. Oof. Now simplify a little bit. These guys cancel. And we get the antiderivative of 1 over the square root of 2 sine theta d theta. So now we are in trig integral territory. Remember that 1 over sine is cosecant. So I can write this as 1 over root 2 times the antiderivative of cosecant, which is not written that way, although you might think it's written that way, cosecant theta d theta. And now this is another one to memorize. This is 1 over the square root of 2 times negative natural log of cosecant theta plus cotangent theta. All right, with that, the calculus is done. And what remains is the trigonometry to take theta, which is something that I made up, and turn it back into x. And the tool for that, once again, is going to be a right triangle with one angle labeled theta. So this here was when I defined theta, and this is so far what I have of my antiderivative. This tells me that sine theta is, we can write this as a couple different ways, x root 5/2, which doesn't really matter. Let's call it x times the square root of 5 divided by the square root of 2. And I know that sine is opposite over hypotenuse. So I'm going to draw my right triangle. I'm going to give one of its acute angles measure theta. My opposite side is here. My hypotenuse is here. And since sine of theta should be x root 5 over root 2, I'm going to put x root 5 in my opposite slot and root 2 in my hypotenuse slot. So now this is an angle whose sine is this divided by that, which is exactly what we're looking for. I want to know the cosecant and the cotangent. The cosecant of theta is 1 over sine theta. And that one's easy enough because we already know sine theta. So this is going to be 1 divided by this number, or if you like, 1 divided by that number. So we can write it as root 2 divided by x root 5. And then for cotangent of theta, this is, let's see, tangent is opposite over adjacent. So this is adjacent over opposite. The adjacent side is not yet known. So I need to use the Pythagorean theorem to find my adjacent side. It's going to be the square root of 2 minus 5x squared. The square root of this squared, which is 2, minus that squared, which is 5x squared. So the cotangent of theta is root 2 minus 5x squared divided by root 2. And now I can translate this back into my original terms of x. This is minus 1 over the square root of 2 times the natural log of the absolute value of cosecant theta, which is this, root 2 over x times the square root of 5, plus cotangent of theta, which is this, the square root of 2 minus 5x squared divided by the square root of 2. That is my antiderivative. So far, we've had the square root of quadratics, and the quadratics were of the form something squared and a constant. Now we're going to see what happens when I have a linear term, something multiplied by x. It doesn't immediately fit any of these three forms. So what I'm going to do is I'm going to complete the square. This is what we do when we want to use trigonometric substitution, but we have something multiplied by x as opposed to just x squareds and constants. So in order to complete the square, first I'm going to notice that the squared term is positive. So my squared term, x squared plus 5x, is going to be something squared, ax plus b squared, plus a constant. If this were negative, I would want this to be negative as well. Let's expand that right-hand side. This is a squared x squared plus 2abx plus b squared plus c. And now what I'm going to do is I'm going to match up the coefficients of each term. So my x squared on the left is multiplied by 1. That means my x squared on the right, this doesn't have x squared, this doesn't have x squared, just this bit, has to also be multiplied by 1. So by matching up x squareds, I know that 1 has to be equal to a squared, so I might as well let a be positive 1. So now this looks like x squared plus 2bx plus my constant term b squared plus c. The next thing I'm going to do is I'm going to match up the coefficient of x. So x is only multiplied by 5. This isn't x, it's x squared. This isn't x, it's a constant. I need 5 to be the same as 2b. So that tells me b is 5/2. So now this looks like x squared plus 5x plus b squared, so 25/4 plus c. And now I'm going to match up the constant term. So if x is equal to 0, this is 0. My constant term is 0. This is plus 0. The constants need to be the same. So I need 25/4 plus c to be the same as 0. So c needs to be negative 25/4. So altogether, I can write x squared plus 5x as a squared term, a times x plus b squared plus c, which in this case is minus 25/4. So I can write this as something squared minus a constant. Now some fine print. We said x squared was positive, so this needed to be positive. We don't have to worry about whether c is positive or negative, because if it ends up being negative, we'll just get a negative number. So the only sign we really have to worry about is the sign of the squared. We have to make sure that matches the sign of the squared part. All right, so now I can rewrite my integral. I haven't done any calculus yet, haven't done any trigonometry. I've just done a little bit of algebra. Now I can see that I have a function squared minus a constant. So I can go up here and find the appropriate identity. This is constant minus a function, that's backwards. This is added, I'm subtracted. Third time is the charm. Squared minus constant, squared minus constant. So this identity on the right is the identity that I'd like to use. Now I need to get the right form of the identity. This bit has an x in it. I can make it into anything I want, but 25/4 is just 25/4. So I need my constant term to be 25/4. So I'm going to multiply this identity on the right through by 25/4. 25/4 secant squared theta minus 25/4 is equal to 25/4 tan squared theta. That's the form I'm going to be using it in. The piece underneath the square root, I would like to turn into this left-hand side. So I would like a substitution that takes x plus 5/2 quantity squared minus 25/4 and turns it into 25/4 secant squared theta minus 25/4. Okay, add 25/4 to both sides. Take the square root, and x plus 5/2 should be, might as well be the positive one, 5/2 secant theta. So x should be 5/2 secant theta minus 5/2. And by writing it in this form, I can take the derivative as well. Dx is going to be 5/2 times the derivative of secant, which is secant theta, tangent theta, and then d theta. This is going to be the substitution that I'll use. Now, if we want to skip some steps, this ought to turn into that, right? Because that was the whole reason we chose this x. But if we just plug in x and go through the motions, by ending up here, we'll have checked our work. So that's the way I'm going to do this. I'm going to just go from here. And if I end up here, then I'll know I've done the correct thing. So in the denominator, x plus 5/2 is 5/2 secant squared theta. 5/2 secant theta. And then I square it and subtract 25/4. And now dx turns into this term, 5/2 secant theta, tangent theta, d theta. So I've got 5/2 times secant theta times tangent theta in my numerator. Underneath this square root, I have 25/4 secant squared theta minus 25/4. And 25/4 secant squared theta minus 25/4. Good, I got what I wanted to get. This can turn into 25/4 tangent squared theta. Now this again is the purpose of doing a trig substitution. I have something squared underneath a square root, so I get to cancel these and get rid of the square root. Now my square root is gone. I can cancel off these tangents and these 5/2, and this works out to the antiderivative of secant, which again is something to have memorized. This is the natural log of the absolute value of secant theta plus tangent theta. And of course, we can add any constant to that. Now the calculus is over. We come back to trigonometry. I need to get this, which is in terms of theta, which is something I made up, back in terms of x's. So this is where our triangle is going to come in handy. Up here on the left is what we have so far of our antiderivative. And this top right bit is how we defined x. So I'm going to take that and I'm going to turn it into the sides of a triangle. So let's find what secant theta is. X plus 5/2 is 5/2 secant theta. So let's multiply both sides by 2/5. 2/5 x plus 1 is secant theta. Secant theta, that's 1 over cosine, so it's hypotenuse over adjacent. I want to write this as one fraction. So I'm going to write this as 2x plus 5 divided by 5. Now I can fill in two sides of my right triangle with angle theta. The hypotenuse side, I might as well call 2x plus 5. And the adjacent side, I might as well call 5. If I want to know secant of theta, that's great. I already know secant of theta. It's tangent of theta I have to worry about. Tangent is opposite over adjacent. So I'm going to want to use the Pythagorean theorem to find the measure of the opposite side here. So the opposite side is going to be the square root of hypotenuse squared, so 2x plus 5 squared, minus 5 squared. So that's the square root of 4x squared plus 20x plus 25 minus 25, which is the square root of 4x squared plus 20x. And if I want to be fancy, I can notice that I can factor out a force. This is the square root of 4x squared plus 5x, which is 2 times the square root of x squared plus 5x. Now I can say that the tangent of theta is opposite over adjacent. That's going to be 2 root x squared plus 5x divided by 5. Opposite over adjacent. So now I can finish my answer. This is the natural log of the absolute value of secant of theta, which is 2x over 5 plus 1, plus tangent of theta, which is 2 root x squared plus 5x, all divided by 5, whole thing plus c. We have one more example to do. We have a square root of a quadratic. There's not an obvious substitution. If this were x to the 1, we'd be delighted. There's not an obvious substitution. We have the square root of a quadratic function, so we start thinking about trigonometric substitution. But I have this linear term, something multiplied by x. I have x squared and a constant, and then that one is in my way. So we are going to need to complete the square. So 6 minus 4x squared minus 4x is going to be a squared term and a constant term. And this is where we have to check signs. Because my squared term is negative, I'm going to be subtracting my squared term, ax plus b squared. So last time we had a plus because our squared term was added. Now it's subtracted, so we have a minus. Let's expand that right-hand side. 6 minus a squared, c minus a squared x squared plus 2abx plus b squared. I'm going to open up these and gather like terms. So this is c minus b squared. Those are both constants. There's no x's. Minus a squared x squared minus 2abx. And I'm going to match up coefficients. Here's my constant. They need to be the same. Here's what's multiplied by x squared. They need to be the same. Here's what's multiplied by x. They need to be the same as well. So let's start with the things multiplied by x squared. So on the left, I have a minus 4 multiplied by x squared. On the right, I have a minus a squared multiplied by x squared. So 4 should be a squared. So we might as well let a be equal to 2. On the left, now let's look at the linear term, say. On the left, I have minus 4 multiplied by x. On the right, I have minus 2ab multiplied by x. That says 4 has to be the same as 2ab, but a is 2, so this is the same as 4b. So that tells me b should be equal to 1. And now finally, I should look at my constant term. On the left, my constant term is 6. On the right, it is not that, but this, c minus b squared. So 6 needs to be c minus b squared, and we saw that b squared was 1. So this tells me that c has to be equal to 7. So altogether, this quadratic equation, 6 minus 4x squared minus 4x, that can be written as c, which is 7, minus ax plus b squared. This enables me to take my quadratic equation and write it as the difference of a squared function and a constant. So I can match that up to one of these. Constant minus something squared, that looks like the first one. This is plus, this is going in the wrong order. So this is the identity that I'm going to be using in my trig substitution. I'm not doing any calculus, just algebra. I'm going to replace this with that. Now I can decide what I should use for a trig substitution. I've got a constant minus something squared, so that's this form. My constant is 7, so the form of this identity I'm going to use is the form I get by multiplying both sides through by 7. My goal is going to be that this term underneath the square root turns into this term on the left of my identity. So what I want is for 7 minus 2x plus 1 squared to turn into 7 minus 7 sine squared theta. That means 2x plus 1 quantity squared should turn into 7 sine squared theta. I'll take the positive square root of both sides. So this is the substitution I want to use. I'm going to need dx though, and indeed I'm going to need x itself, so I'll go ahead and finish solving for x. Subtract both sides by 1. And now divide through by 2. Now I can find what dx is going to be. It's going to be root 7 divided by 2 cosine theta d theta. This is the substitution that I'm going to use. Now, if I plug this in here, and I haven't made any mistakes, this green bit should turn into that green bit. In the past, in this video, we've done that to check ourselves, but this time, in the interest of time, we'll just believe that we did this correctly and that we haven't made any mistakes. So on the top, x squared, that's going to be this squared, root 7 divided by 2 sine theta minus 1/2, that's x, and it gets squared. And in the denominator, I specifically chose my x so that this would turn into that, 7 minus 7 sine squared theta. Now, since I'm substituting, I also need to translate my dx. My dx turns into root 7 divided by 2 cosine theta d theta. In the denominator, underneath that square root, I get to use my identity and turn this into 7 cosine squared theta. So in my denominator, I get the square root of 7 cosine squared theta. And again, that's what I'm going for. I'm going for the square root of something squared, so I can cancel these off. I'll expand the top, and we get 7/4 sine squared theta minus root 7 over 2 sine theta plus 1/4. And then I'm still multiplying by root 7 over 2 cosine theta d theta. So now let's turn the denominator into root 7 times the cosine of theta. I can cancel some things out now. I can cancel out the cosine theta, and I can cancel out this square root of 7. So what I'm left with is, I've got this 1/2, so I'll push that through, 7/8 sine squared theta minus root 7 over 4 sine theta plus 1/8. With theta as my variable. All right, now I am in trig integral territory. We've talked about evaluating powers of science. So now we get to finally do the calculus step. I'm going to cut this into 2 integrals because even powers of sines and cosines work a little differently. So I'm going to call this 7/8 times the antiderivative of sine squared theta plus the antiderivative of root 7 over 4 sine theta plus 1/8 whole thing d theta. For the left, I'm going to use, remember here we use the half angle formula. Sine squared is the same as 1 minus cosine of 2 theta divided by 2. On the right, I can just anti-differentiate. This is minus root 7 over 4 cosine theta plus 1/8 theta plus c. So now I anti-differentiate what's going on the left-hand side. There's that 1/2. The antiderivative of 1 is theta. The antiderivative of cosine is sine, but it's 2 theta, so I need to multiply by 1/2. All right, so now I have done the calculus part. I've gotten my answer, but unfortunately it is in terms of a variable that I myself have created and not a variable that was asked in the question. So I'm going to need to use some trig to translate these thetas back into x's. So in order to do that, I should remember where theta came from. So I need to scroll back and look at my substitution. Here's my substitution. This is where I defined the relationship between theta and x. So let's put that here. All right, sine of theta should be easy enough to find, but sine of 2 theta is a little bit different. So we're going to use the double angle formula here as we ordinarily do. So I've got theta minus 1/2 sine 2 theta is the same as sine theta cosine theta. Sine theta I can find by just solving. X plus a half is root 7 over 2 sine theta, multiply through by 2, 2x plus 1 is root 7 sine theta, divide through by sine theta, divide through by root 7. 2x plus 1 over root 7 is sine theta. So this is good. For the cosines of theta, I can use my right triangle. Theta is some angle. Its sine is 2x plus 1 over root 7. And remember, sine is opposite over hypotenuse. So I'm going to label the opposite side 2x plus 1, and I'm going to label the hypotenuse root 7. In order to find cosine, I need adjacent over hypotenuse, so I'm going to use the Pythagorean theorem to find the measure of the adjacent angle. So that's root 7 squared minus 2x plus 1 squared. And I'm just going to simplify this a little bit. 7 minus 4x squared plus 4x plus 1. That's 6 minus 4x squared minus 4x. So now when I want to find cosine, it is adjacent over hypotenuse, but I also have just a theta. Now, if we have sine, cosine, tangent, cotangent, cosecant, or secant of theta, we can figure out how to go from theta to x using this right triangle. But if we just have a theta, we can't avoid having some inverse trig in here. So from this point, I can take the arcsine of both sides, and that tells me that theta is the arcsine of 2x plus 1 over root 7. Just a quick note, the sine of the arcsine of something is just that something. And so you never want to write it this way because arcsine of something is generally very difficult to figure out. So when you write it this way, if you wanted to actually evaluate this, you would first have to evaluate arcsine, which is tough, and then evaluate sine, which is also tough, as opposed to just saying, I know what the answer is. So that's why you never want to write sine of arcsine. And similarly, you don't want to write sine of arccosine. You never want to have trig of arctrig. So I never want to plug this in here. But if I don't have a trig function glued onto my theta, if I just have theta, there's no way around this inverse trig. So altogether, this is 7/16 times theta. Theta is the arcsine of 2x plus 1 over root 7. Minus sine theta, which is 2x plus 1 over root 7, that's here, times cosine theta, so that's adjacent over hypotenuse, or root 6 minus 4x squared minus 4x over the hypotenuse, which is root 7. So that's cosine theta right here, minus root 7 over 4 times cosine theta, which is again adjacent, root 6 minus 4x squared minus 4x divided by hypotenuse, root 7, and then plus 1/8 theta, so 1/8 arcsine 2x plus 1 over root 7 plus c. And that is my antiderivative.